Hello to everyone watching. Today I'll be speaking about Apache Cassandra, ScyllaDB, and their evolutionary differences. My name is Peter Corliss. I'm the Director of Technical Advocacy at ScyllaDB. I listen to our user stories, and I discover wisdom in each to share with our other practitioners in the industry at large, whether through blogs or in technical presentations. A little bit about ScyllaDB, the company, and our product, ScyllaDB, the real-time big data database. We're a company of more than 100 employees located around the world. ScyllaDB, our database, is a fully distributed, highly available NoSQL database, fully compatible with both Apache Cassandra and Amazon DynamoDB APIs, perfect for your most data-intensive applications. Because of its advanced architecture, ScyllaDB provides superior system utilization, resulting in higher performance, lower latencies, and better ROI on your infrastructure. ScyllaDB is available as pure open source, which we'll be talking mostly about today. We also have an enterprise edition with value-added features and full enterprise support, plus a fully managed database as a service, Scylla Cloud. Speaking about those APIs, today we're going to compare ScyllaDB to Apache Cassandra, its CQL interface to CQL interface, using some objective observable analysis from software release cycles to GitHub commits. Plus, for those of you for whom this is a first webinar with us, I want to go over some history of how we began as a Cassandra compatible work-alike, and now we're moving beyond Cassandra's capabilities. Also, to be clear, I want to come here today to clearly shatter an illusion, that of the drop-in replacement. Yes, I know that we at ScyllaDB have ourselves often said that we're just that, a Cassandra drop-in replacement. And in many ways, it is true. But I want to point out that while there are many similarities, there are also many points of departure in design, in implementation, and in capabilities. And so it's not an exact same replacement. Lastly, I want to share with you some benchmarking results from tests we conducted, both Cassandra 3.11 against its own successor, Cassandra 4.0, as well as against Scylla Open Source 4.4. And let me level set us for any first-time attendees with what ScyllaDB is and does. ScyllaDB is a NoSQL database of the wide column family, perfect for monstrously scalable, highly available data-intensive apps, terabyte to petabyte workloads, millions of operations per second. You've come to the right place. It uses a partitioning key to distribute data as evenly as possible across the cluster, and a clustering key to make data rows within partitions sortable. My colleague Nadav Harel is fond of describing wide column databases like ScyllaDB as a key value database. And yes, you can, and many people do, use ScyllaDB as a basic key value store. Next, the whole reason for ScyllaDB being written in the first place was to showcase how database infrastructure can be written for far more efficiently for modern multiprocessor, multi-core systems. Because even a single computer server these days constitutes its own network within the box itself, with hardware servers capable of sporting well over 100 cores or possibly into the thousands. You need database infrastructure that can take advantage of all that silicon. Traditional database designs, you just couldn't get maximum utilization out of your hardware. Yet using ScyllaDB, you can now get the best ROI out of all your infrastructure investment. So how do we change the game? ScyllaDB was written on the C* framework that has a shard per core, async everywhere, shared nothing design using all the latest C++ tricks like features and promises. Basically, once you presume Linux as your operating system of choice, the advantage of being written in a write once run anywhere language like Java is obviated. Plus, what stop the world garbage collection pauses, the Java codebase itself is a production liability. Sure, it's facile to write, but it's just not designed for performance optimization. While ScyllaDB was originally designed to replicate the Apache Cassandra interface, we've also added a DynamoDB compatible API called Alternator. However, for today's talk, I'll focus exclusively on the Cassandra and ScyllaDB Cassandra compatible feature sets. Historically, since ScyllaDB released, we have been perceived as chasing Cassandra, working to achieve feature parity. So this meant that through 2020, we were playing catch up. However, with Scylla Open Source 4.0, we went beyond feature completeness. We suddenly had features Cassandra didn't even have at all. Plus, we had features that might have a similar name, but we implemented them differently, often radically so. Lastly, the Apache Cassandra developers will naturally keep adding commands, new features and formats, For example, the SS tables format changed once between 4.0 beta and release candidate 1, and then again in the final release. What this results in is the following kinds of buckets of features. Many core features of Cassandra were also implemented in the ScyllaDB core, the same configuration, same command line inputs and outputs, same wire protocol, and so on. Then there were some things that are unique to Cassandra. For instance, the Cassandra 4.0 features. Some of these we plan to add in due time. Some simply may not be appropriate to implement because of the very different infrastructure and design philosophies, even the code bases. For instance, you won't find Java-specific features like new garbage collectors or netty as you would have in Cassandra. Inversely, you'll have some features in ScyllaDB that they just won't implement in Cassandra, like ScyllaDB's DynamoDB API. Lastly, there's a mix of features that may be called by the same name or may sound quite similar, but are actually implemented uniquely across Cassandra and ScyllaDB. We'll get into some of those, like the way each database implemented change data capture. These are all points of divergence which could become showstoppers for migration if you depended on them in your use case, or they may be specific reasons to migrate to the other database if they represent features or capabilities the other database will just never offer you or offer in a better way, and you really need them. So while ScyllaDB began by chasing Cassandra, now many of our features are beyond Cassandra. And while we remain committed to making our database as feature complete and compliant to Cassandra as possible and pragmatic, it will be quite interesting to watch as current points of departure between the two become narrowed or widened in the coming years. Before I get directly into the features and functions, I also want to back up and talk about two major differences between these two databases. First, comparing software release cadence, and then second, comparing public perceptions. Because beyond specific hair splitting of how you store files in a file system or shove data into and out of memory, databases exist in a world where the surety of business commitments and community trust factor directly play into your strategic decision-making. When you make a database switch, you want it to be one that you're happy with and you're not going to change out for a long time. Ironically, the opposite can also be true. There can be infrastructure code that you stick with, not because you're happy with performance, but because the new version just hasn't shipped yet. And this was the case with Cassandra in that historically long pause after 3.11 released. I remember talking about Cassandra 4.0 in 2019 and in 2020. By 2020, Cassandra 4.0 had finally reached beta, where it would then linger for another calendar year. It even missed the deadline for its own world party in April 2021, but at least there was a release candidate. So in many ways, I was just as excited and relieved as anyone in the industry when I heard that it really was finally here in July 2021. But that was 4 long years between the last Cassandra minor release and this new major release. And that's a hell of a long time in database years. Also, I'm glad to note that the first Cassandra 4.x maintenance release also came out in September 2021, which means that they're establishing a new cadence for software release. And let me show you why that's important. Here you can see the calendar of milestone releases for Cassandra and ScyllaDB as of today. You can just see that glaring multi-year chasm between the release of Cassandra 3.11 and Cassandra 4.0. If you go back earlier to the last major release of Cassandra 3.0, you can see that it was back in 2015. That was around the time that the Scylla open source GitHub repository was being created. We were on release 0.1.0 around then. So over that same historical span of time, ScyllaDB was birthed into the world and has had 4 major releases. And within those major releases, multiple minor releases, as well as dozens and dozens of maintenance releases. For example, since May 2020, we've put out 5 minor releases for Scylla Open Source 4.x alone, and 4.6 release candidate just went out last month. Plus soon we'll have Scylla Open Source 5.0 out the door. And so why is this important? Because it shows the velocity of your software supply chain. It shows how quickly you can innovate. It shows how quickly you can close critical bugs. It was one of the main reasons some companies like Expedia felt that they could trust ScyllaDB more than Cassandra, simply because of a dependable, regular software release cadence. Putting it another way, if we're living in a world of continuous integration and continuous deployment, why did you have to wait over 4 years for a monolithic major software delivery of your core database? Next, on top of our Scylla open source releases, we have an annual cadence of enterprise releases with additional testing, additional features, and additional customer expectations for stability. In most cases, our users will see new features and capabilities in early deployment in Scylla open source first. Then, as they mature and harden, we'll move them to general deployment or GD status, and only then will you see them sink down into an enterprise release. There are also some special enterprise-only features, which I won't get into today, but just know that we're running these two trains side by side. Beyond just a release cycle, users watching open source repositories can see the velocity of development in the number of commits per week. ScyllaDB has at times exceeded 100 commits per week. You might also be surprised to discover that across 2021, there were about 50% more people committing to Scylla open source as to Apache Cassandra. In terms of those minor and major release cycles made between 2018 and today, Apache Cassandra is the only major release that they have had across that period of time. Whereas the ScyllaDB team pumped out a baker's dozen of freshly baked software releases. ScyllaDB now has more GitHub stars than Cassandra, and the gap between the two is widening. So there's a lot of ScyllaDB curious people out there, and we'd love to see them spin up a cluster. But now let's take a look at how you, the public, users, and developers view Cassandra and ScyllaDB. An objective industry measurement is kept by the folks at dbengines.com. They scour a number of different sources, from the quantity of Google searches and page results for the terms Apache Cassandra or ScyllaDB, plus mentions of database skills in online job postings or in your LinkedIn profile. So the dbengines.com ranking is a handy way to see how much mindshare there is for your favorite database in the industry at large. In their rankings of all the major databases of the world, Cassandra has often been in the top 10, though in January of 2022, it dipped just below that to now sit at number 11. Meanwhile, ScyllaDB continues to advance rapidly and now ranks in the top 100 databases that dbengines.com ranks. We're currently ranked at number 85. Plus, out of the top 100 databases that dbengines.com tracks, we were the fourth fastest growing database in terms of year-over-year score percent increases. And yes, that is a log scale graph. So Cassandra currently with a score of 123 is over 30 times more popular than ScyllaDB with a score of just under 4. So we still have plenty of work cut out for us. By the way, before I move on, if you haven't added ScyllaDB to your LinkedIn profile, please go ahead and do so. It's a great way to help us out. Remember how I said Cassandra used to consistently be in the top 10 and how I mentioned that release cadence affects public perception? You can see Cassandra's trend line more pronounced in this graph view. That long gap between releases between 2017 and 2021 really did erode public interest, appeal, and trust. Its score dropped 20% over those 4 years. Yet, since Cassandra 4.0 released, you can see that marked increase again in its rankings. So while Cassandra hasn't fully recovered its former glories of 2017, the 4.0 release has definitely helped recover some of the sheen that made it so popular to begin with. So with that context as a preface, now we can get into the specific technical features. Let's start with the common ground. If you're familiar with Cassandra today, what can you expect to feel as comfortable and as natural in ScyllaDB? First, the common ancestry. Many of the principles between Cassandra and Scylla are directly correlated. In many ways, you can call Cassandra the mother of ScyllaDB in our little database family tree here. Though remember, we also pull in some of our DNA from Amazon DynamoDB. The highly available architecture Cassandra is known for is also found in ScyllaDB: peer-to-peer, leaderless topology, replication factors and consistency levels set per request, multi-data center replication, which allows you to be able to survive a full data center loss, all typical AP mode database behavior. Plus, if you have the same underlying ring architecture, the key value scheme of a wide column database, partition keys and clustering keys, nodes and vnodes, automatic sharding and the Murmur3 partitioner. The concepts of key spaces and tables is all pretty much standard CQL here. Basic CRUD operations as well, all quite familiar, comfortable as your favorite sweater. By the way, another way ScyllaDB is compatible with Cassandra is that you can use all your same Apache Cassandra and DataStax drivers. They just work. This is an advantage for when you want to change out your backend without even touching your client apps or drivers. Your dev team won't even know or care. They'll just be glad to see the lower latencies and higher throughputs. Now, a vanilla CQL driver won't take full advantage of ScyllaDB's shard-aware architecture. They won't be optimized to consume our CDC data, but they'll work. Before I go into the next section, I just want to take a moment for another quick audience poll. For a sense of scale, I'd like to understand how much data do you have under management in your own transactional database systems? Please pick the answer that best matches your current data set. Less than 1 terabyte, between 1 and 50 terabytes, 50 to 100 terabytes, or greater than 100 terabytes. We'll leave the poll up for a bit of time for you to answer. Also remember to use that Q&A feature to ask your questions at any time. I'll answer them all at the end. Thank you. While there are still more features that are alike, let's not be exhaustive. Let's check out all the things that seem similar between the two, but really are just not the same. CQL, that's right. Cassandra query language implementation itself. While most of the basic commands are the same, you will note ScyllaDB may have implemented CQL commands that do not appear in Cassandra, or vice versa. There's also version level completeness. For example, Cassandra's CQL is up to, last I checked, 3.4.5, while ScyllaDB's implementation is only at 3.4.0. What are the specific differences between them? I'll let you scour the docs as a homework assignment. While some of you may find that these are really pretty trivial differences, if you are migrating between the two, any unexpected differences might represent an unpleasant showstopper until we finally reach CQL parity and completeness again. Next, SS tables. ScyllaDB is compatible with Cassandra 3.11's MD format. But did you spot the difference with Cassandra 4.0? In the first release candidate, they snuck out the NA format, which added a bunch of small changes. And then when 4.0 shipped itself, they added a way to store the originating host ID in NB format SS tables. We've opened up a GitHub issue to make sure ScyllaDB will have NA and NB format compatibility in due time, GitHub issue 8593. We also have an issue for open for the new ME format SS table format, which also uses that originating host ID. And check out GitHub issue 9869. This is the sort of common everyday feature chasing you have whenever anything releases a new version, anytime you spin new software. And everyone else needs to ensure compatibility. There's always a little lag and gap time before implementations. It's understandable, albeit inconvenient. Lightweight transactions, or LWTs, are pretty much the same sort of thing on both systems to do compare and set or conditional updates. Both use a Paxos consensus algorithm to accomplish their work. But on ScyllaDB's LWTs, they're simply more performant because instead of taking 4 round trips, as with Cassandra, we only require 3. And what this has led to in practice is that some folks who have tried LWT in Cassandra, only then to back them out when performance tanked or didn't meet expectations, they can now experience LWTs in ScyllaDB. You can try them again, and they might actually have the performance that you were expecting when you first did your experiments. Materialized views, or MVs, are another case where ScyllaDB put more polish into the apple. While Cassandra has had materialized views since 2017, they've been problematic since first introduced. At Distributed Data Summit 2018, Cassandra PMC Chair Nate McCall told the audience that if you have them, take them out. I remember sitting in that audience, absorbing the varied reactions as Nate spoke frankly and honestly about the shortcomings in the implementation. Meanwhile, the following year, ScyllaDB introduced its own implementation of materialized views. They served as the foundation for other features, such as secondary indexes. While MVs can still get out of sync from the base table, it's not as likely or easy to do. ScyllaDB engineers have poured a lot of effort into the past few years to get materialized views right, and we consider the feature ready for production. Speaking of secondary indexes, while you have them in Cassandra, they are only local secondary indexes, limited to the same base partition. They are efficient, but they don't scale. Global secondary indexes, which are only present in ScyllaDB, allow you to index across your entire data set, but they can be more complicated and they can lead to unpredictable performance. So you want to be more judicious how and when you implement them. The good news for ScyllaDB is that it supports both local and global secondary indexes, and you can apply both on a column to run your queries as narrow or as broad as possible. Change data capture, or CDC, is the most dramatic difference between Cassandra and Scylla. Cassandra implements CDC as a commit log-like structure. Each node gets a CDC log, and then when you want to query them, you have to take these structures off box, combine them, and dedupe them. Now, if I misunderstand, please follow up with me afterwards. I'd love to hear how Cassandra practitioners are using CDC. But think about the design decisions that went into ScyllaDB's CDC implementation. First, it uses a CDC table that resides on the same node as the base table data, shadowing any changes to those partitions. Those CDC tables are then queryable using standard CQL. So the results are that your results are going to be deduped for you. There's no log merges necessary. You get a stream of data, whether that includes the diffs, the pre-image, or the post-image, however you want to consume it. Plus, we also have a TTL set on the CDC tables so they don't grow unbounded over time. And this made it very easy for us to make a Kafka CDC source connector based on Debezium. It simply consumes the data from the CDC tables using CQL, and it pumps it out to Kafka topics. No muss, no fuss. And here's another example of a point of departure. Cassandra historically had problems with streaming SS tables. This can be important when you're doing topology changes and you need to bring up or down nodes and rebalance your cluster. Zero copy streaming means that you can take whole SS tables, all of its partitions, and copy it over to another node without breaking an SS table into objects, which creates unnecessary garbage which then needs to be collected. It also avoids bringing the data into user space on the transmitting and receiving nodes. Ideally, this was all to get you closer to hardware I/O bounds. ScyllaDB, however, already had radically changed how it was going to do internode copying. We use a road-level repair-based mechanism instead of standard streaming methodology. This was more robust, allowing midpoint stops and restarts of transfers. It was more granular, meaning you were only sending the needed rows instead of the entire table, and so it was more efficient overall. So these are fundamentally different ways to solve the problem, and I'll show you the results of these different approaches when I get to the benchmark section. Netty async messaging is a good thing. Any way to avoid blocking and bottlenecking operations is awesome. Also, the way it does thread pools means that you weren't setting a fixed number of threads per peer, which could mismatch real-world requirements. ScyllaDB has always believed in non-blocking I/O. It's famous for its async everywhere C++ architecture. Plus, the shard per core design means that you are minimizing intercore communications as much as possible in the first place. Again, these were good things, but for Cassandra, it was an evolutionary realization they wove into their existing design, whereas for ScyllaDB, it was a day one design decision, which we've improved a lot upon since. In summation, it's doing sort of the same thing, but in very different ways. Kubernetes. Cassandra now has a range of options for Kubernetes, from DataStax's Cassandra, which replaces the now deprecated Cass operator, or Casscop by Orange, to Bitnami charts. If anyone has feedback on any of these in particular, I'd encourage you to contact me after this talk. I'd love to learn from you, your experience. For ScyllaDB, we have our own Scylla operator. Our users like it just well. So yes, Kubernetes is available for both, but each operator is purpose-built for each respective database. Now let's take a look at things that are just simply different, right? From fundamental design decisions to implementation philosophies, to even the vision of what these database platforms are and can do. A critical day one decision for ScyllaDB was to build a highly distributed database upon a shared nothing shard per core architecture. You may have heard of the C* framework. You can scale it up, scale it out, or both. ScyllaDB is a greedy system. It will gladly utilize whatever resources you grant to it. ScyllaDB is designed to make maximum utilization out of all the hardware you can throw at it. Because of this, ScyllaDB can take advantage of any size server. 100 cores, sure. 1,000 cores, don't laugh. I know of a company that's working on a 2,000 core system, and such hyperscale servers will be available before you know it. In comparison, Cassandra shards per node. It also gets relatively low utilization out of the system it's running in. That's just the nature of a JVM. It doesn't permit you knowledge of or control over the underlying hardware, which is why people seek to run multi-tenant in the box to utilize all those cycles that Cassandra just can't harness. ScyllaDB's shard-aware design paired with token-aware drivers means that you can direct queries to the specific core on the specific node that has your desired data. ScyllaDB as a server already provides you performance improvements over Apache Cassandra, but adding these shard-aware drivers means that you can squeeze out even more performance by routing queries directly to the right node, which means less random connections and less hops and less work for the coordinator nodes, which means that you get maybe 10%, maybe up to 25% greater performance just by having these shard-aware drivers. Plus, our drivers are still backwards compatible with Apache Cassandra. The leading example of our new shard-aware drivers is our Rust driver. We'll have a great session at Scylla Summit 2022 in a month from now, where you can learn and how it will serve as the basis for a whole new generation of drivers. And if you don't even want to wait a month, you can download the Rust driver today from GitHub. There are many, many other things I could have picked out, but I just want to show this one as another example of a quality of life feature for database administrators. Seedless gossip. There's been a lot of pain, a lot of suffering. If you lost a seed node, it requires manual assignment. Seed nodes just won't bootstrap themselves. It can cause a lot of real-world, real-time frustration when your cluster is at its most temperamental. So one of our engineers came up with a brilliant idea of just getting rid of seed nodes entirely, reworking the way gossip is implemented to be more symmetric and seamless. And I hope you have a chance to read this article about how it was done. I promise it's pretty juicy. Here's something else Cassandra just doesn't do and has no plans to do. Alternator. It's our name for the Amazon DynamoDB compatible API we built into ScyllaDB, which means that now you have freedom. You can still run your workloads on AWS, but you might find that you get a better TCO out of our implementation running on our Scylla Cloud Database as a Service instead. Or you might use it to migrate your workloads to Google Cloud or Azure, or even put it on premises. An interesting example of the latter is AWS Outposts. These are cages with AWS servers installed in your own premises. These servers act as an extension of AWS into your on-premises environment. Because we were capable of being deployed anywhere, ScyllaDB was chosen as AWS's method to deploy your DynamoDB workloads directly into an AWS Outpost environment. Getting back to our alternator implementation, using our CDC feature as the underlying infrastructure, we also support DynamoDB streams. Plus, we have a load balancer to round out many of the same expectations of existing DynamoDB users. And lastly, our Scylla Spark migrator makes it easy to take those DynamoDB workloads and place them wherever you desire. I also wanted to take a little bit of time to talk about our implementation of Raft. Now, to hear the real inside scoop on our Raft implementation, you definitely want to come to Scylla Summit. Again, February 9th and 10th. It's online, it's free. You can register at ScyllaDB.com/summit. But here's some wave tops. With our Raft implementation, you're going to find it a lot easier to make schema changes. And with our Raft-driven topology changes, you're going to be able to add multiple nodes at once. No more spinning up nodes serially. Now you'll be able to fire them all up at once, and the streaming and rebalancing will happen in the background. So next, let's get down to more hardware numbers. These benchmarks were published back in August 2021, so they're still pretty current. The first thing to note is that throughputs for Cassandra between 3.11 and 4.0 aren't that much different. And in all cases, they're significantly lower than what ScyllaDB could achieve on the exact same hardware, about 2 to 5 times slower. There are some workloads for Cassandra 4.0 that saw improvements of 25% or more, up to 100% improvements for a high cache hit rate scenario. But for many tests, the achievable throughputs for Cassandra 4.0 over Cassandra 3.11 didn't budge much at all. What did radically change for Cassandra 4.0 were the latencies. In some cases, P99 latencies dropped by 95 to 99% between Cassandra 3.11 and Cassandra 4.0. But even then, in many cases, the latencies were often still far higher than ScyllaDB, up to 100 times worse. So sure, if you are running Cassandra 3.11, under many conditions, it will make sense to upgrade to Cassandra 4.0. You will see massive latency drops and, depending upon the workload, some significant performance gains. But now, having waited patiently into 2021, are these performance gains sufficient to warrant recommending Cassandra 4.0? In many cases, it just makes more sense to migrate to ScyllaDB or just start there for a greenfield project. Let's look at throughput versus latencies. In this use case, you can see how Cassandra's long tail latencies went nonlinear really quickly in the 30K to 40K operations per second range. ScyllaDB, meanwhile, continued to scale far more linearly and kept P99 latencies lower than 10 milliseconds out to around 170K operations per second, providing 4 to 6 times the throughput, all on the exact same hardware. Replacing a node. I hear it happens in actual production networks from time to time. So here you can see that while zero copy streaming and other performance improvements in Cassandra 4.0 definitely do provide benefits, some speed improvements, it's still going to be multiple times slower than ScyllaDB can perform the same node replacement. Why are you waiting more than 3 hours in a day to replace a single node when you can do the same operation on ScyllaDB in less than an hour? Because while you're busy streaming, you're still down a node with your performance suffering a low-grade fever until the cluster finally rebalances. This real-time delay is even more pronounced if you need to scale a cluster by more than one node. Say you want to double capacity. With ScyllaDB's faster per node provisioning, you can double the entire cluster, the whole thing, faster than it would take Cassandra's 4.0 to even get the first node up and running. But this is a killer. Look at this closely. Your eyes might have missed that first blue bar in the chart. That's ScyllaDB. ScyllaDB optimizes compaction speed so much that it can run compactions in all of 36 minutes on a 3-node cluster. Boom, done. Meanwhile, Cassandra can take nearly a day, even after we tuned it. By default, it took a day and a half to run compactions. So yes, with tuning, Cassandra 4.0 is moderately better than Cassandra 3.11, but why are you needlessly inflicting pain and suffering on your DevOps team? Okay, in this test, we decided to switch things up. Rather than run on the exact same hardware, which we did with the earlier test, this test ran on clusters more optimized for the respective databases. Here we chose i3 metal instances for ScyllaDB because ScyllaDB, written in C++, can run close to the metal. Whereas Cassandra, written in Java, still doesn't have full utility of the server it's running on, even with the newer JVMs. They are better, yes, but you're still walled off from truly understanding the hardware you're operating on. So in this case, we have Cassandra on i3 4x large instances. We gave Cassandra 40 of those for 640 vCPUs total. Meanwhile, ScyllaDB was on only four i3 metals. So that only had 288 vCPUs, less than half of the Cassandra test cluster. But ScyllaDB was able to maintain the same or better performance, even being outgunned, because we really take advantage of every CPU cycle we can get our hands on. What resulted was this 60% savings in total cost of ownership, but also a reduction of 90% of the administrative burden and the security attack surface, right? You simply had 1/10 of the nodes to watch over. which makes a difference as you continue to scale. So these are the links to the published benchmarks, which you can find on our website. You can also watch the on-demand webinar we did with our engineers who ran the benchmark. The Q&A that followed was also really engaging, and I think you'll get a lot of insight out of it. It goes into far more depth than I can cover here today. And with that, thank you. You can always follow with me at Peter Corliss on Twitter. And if you want to learn more about ScyllaDB, our highly available, monstrously scalable database, again, check out the free online courses at university.scylladb.com. And now let's get into some Q&A. We have a question from Ion. He would like to hear a little bit more about automatic sharding in both Scylla and Cassandra. Okay, let's start with that. So automatic sharding has been around for a long while in the NoSQL world, especially. You know, again, it used to be that you'd have to manually shard, and like the original manual sharding was like, you know, let's take a database alphabetically split up, and you'd have A's on one shard and B's on the next. And of course, that makes for really imbalanced sharding because there's probably going to be a lot more A's and B's than you have Q's and Z's. You know, those are just not used a lot in let's say surnames, right, or first names. So you want to have an automatic sharding mechanism that's going to balance the cluster as evenly as possible. Now, not all data is the same, so you still may have hot partitions, right? You may have large partitions. You know, this one's got a couple of K, this one's got a couple of K, this one's got 50 megabytes in the partition, right? So you can still have hot or large partitions. But Scylla and Cassandra both use that Murmur3 partitioner to kind of come up with a token infrastructure, token architecture to as evenly spread your partitions across the cluster as possible. And again, that's all part of the auto sharding. There's a lot more that we can go into. You can definitely read more about our sharding mechanisms on our website. So that's just a little bit more. I hope that solves the issue. And then the next question I have, CDC table sitting on the same node as the base table is a little confusing. What exactly do you refer to as sitting on the same node? Okay, right. So what's happening is that as a partition is changing, right? So let's say there's a row that changes in a partition. That change is captured in, I think it's based upon the same materialized view kind of infrastructure, right? So there's a CDC table that's created that is, you have to specify like which table you want to track for CDC. But once you specify that, then on the same shard, right, and the same pinned to that CPU, there'll be a table that's related to the base table that will keep track of the changes. So row here changes, I'll shadow that. And again, you can specify what was the difference, or what was the whole post image, or what was the pre-image. Like you can specify any or all three of those as to what you want to capture in the CDC table. And so that'll remain on, again, on the same kind of shard. And so yes, that means that there's going to be a lot more of these SS tables that are shadowing your base SS tables. And so that's why we wanted to make it readable through CQL so that it's going to do the deduping from, you know, wherever the nodes are that you're making the query. Potentially you're doing some full table scan or something like that. We wanted to make sure that that the CDC table is going to have data as close to it as possible for performance. But again, it would be easy to consume using the CQL interface, as opposed to, again, the other implementation was you have all these commit logs on every node. You got to download them, suck them down at some period of time. You then got to, you know, collate them somehow, dedupe them, you know, to get that view of what's changed. So I think that our implementation is far more elegant. I hope that answers your question. Let's see. Would have been nice to know what volume of data we are talking about when replacing a node happens. I think all of those, it's in the benchmark. They're all like 4x cells, I think it was. So I think that they were all like something like at least a terabyte per node. So, but you can read the benchmark to see exactly how much data was per node when it was doing its rebalancing then. I'm sorry, yeah, you're right. That's a good point. We should add that the next time we do this talk. We have another question here. what's the difference between ScyllaDB's and Cassandra's repair times and methods? So again, with Scylla's repair mechanism, it's a row-based repair mechanism. So we're not repairing an entire SS table at a time, right? We're doing row-level repair. And so that means that we can do the operation a lot more atomically because we have this capacity to kind of start and stop repairs. You know, we can schedule them better so that, let's say you're running on some sort of peak workload right now, you're getting a lot of reads, a lot of writes, a lot of transactions coming through. Maybe you want to stop repair for a little bit, wait for that system to quiesce, then you can start the repair time. So again, this was built into our whole row-based repair mechanism. And I believe that we have a log on our website about that if you want to read more. It's definitely a really interesting feature. And what's the difference between them? Again, Cassandra doesn't have that row-based repair. It's going to try and be repairing entire SS tables at a go. So I think that's the answer with that. Is the performance comparison applicable to DataStax Enterprise Cassandra or just Apache Cassandra? Well, as far as I know, and people who are the DataStax experts out there can inform me differently, but as far as I know, DataStax DSC is still based upon Cassandra 3.11. Now, I believe that they're probably working hard right now to get it compatible with Cassandra 4.0. But I don't think DSC is a 4.0 compatible database yet. Now, I'm sure a lot of people are waiting for that to happen, and then you'll get the same speed improvements with that you get with Cassandra 4.0. But until that happens, you're still going to be seeing numbers more closer to 3.11, I would think, right? Now, you know, I would like to see DataStax produce their own numbers. I don't want to second guess them, and maybe they do have some better performance than vanilla 3.11. But as far as I know, it should be closer to that than the 4.0 infrastructure. Again, I'm just guessing. I'm not a DataStax expert. If you're in there in the chat and you'd like to chime in, let me know. Let's see. I'd like to ask regarding the low cache hit benchmark. As far as I know, Cassandra allows to have key row cache tuned separately, while Scylla relies upon LRU row caching without an option to cache keys. So yeah, we have a row-based cache, right? So we don't keep separate caches. We only have the single unified row-based cache. So in a way, ours is far more efficient. You don't have multiple number. Like for instance, let's say you had a cache miss, right? So Cassandra could potentially slow you down by checking one cache, oops, wasn't there, checking another cache, up, still didn't find it, now I'll finally read to disk. You could hit, you know, multiple different caches that way, whereas Scylla with only the single unified row-based cache, if it's not there, boom, it goes straight to disk. So we can at times be a far more efficient cache system. Let's see, so having this in mind, it seems to me Cassandra should behave better on low cache hit rate ratio. Yeah, again, I think that's the reason why we went out though, is because we have this the single just the single cache. So you check, and if it's not there, boom, you go straight to disk. By the way, I think we also have bypass cache. So like if you're doing a full table scan, it makes no sense to be checking your cache anyway. So we have a bypass cache command. You can go straight to disk. You know, and again, that could be set per query. Okay, so that's some great questions, folks. I wanted to thank everybody for being here. And with that, have yourself a great day and onwards to adventure.